Hello everyone. Here in this video, we are solving a problem basing on the concept of surface tension. Let us first read out the problem to understand that what we are trying to find out. The problem is like this. A large number of liquid drops, each of radius b, collides to form a single spherical drop of radius a. Let me stop here for a minute and understand what is being given for us. What he said is, there is large number of drops. I don't know how many is that large number. Let that number is n. Let n number of drops each of radius b are combined, merged to form a big drop of radius a. So when large number of the drops are combined to form a big drop, there is some kind of the energy released in the process. How much is that energy released? That's what we want to calculate. Before going to talk about the energy aspect, let me say, as small drops are combined to form a big drop, what is always conserved is mass. Density equal to mass by volume. Density is constant. That implies mass conserved means volume is conserved. What do you mean by volume is conserved? Volume of all small drops together. Let assume volume of each small drop is S. Like that, there are n number of the drops. So all volume of the n drops together equal to the volume of the big drop. Being the drop is spherical, volume can be written like 4 by 3 pi r cube. Radius of each small drop is b. So 4 by 3 pi b cube is volume of the big drop, 4 by 3 pi a cube. So 4 by 3 and 4 by 3 pi can cancel. So a cube equal to n into b cube. That's one relation we have got. A cube equal to n into b cube. So basing on the first statement, we can get this, right? Relation between A and B in terms of number of the terms, we have got it. Now, so what he's saying is all these n drops are combined, merged to form a big drop of radius A. In that case, we can get this conclusion. A cube is equal to n into B cube. Let's proceed back to our problem, right? The energy released in this process is, right? So what happens next we will talk later, but first let's talk about this part. The energy released in this process is, we will try to find out what is the energy released in this process is, right? We know the very definition of surface tension in terms of the work done as surface tension as work done by change in the surface area. Work done to increase the unit surface area of a liquid can also be called as surface tension. We have defined this, we have explained this. You can go back to the previous concepts of this playlist to get this information if you are not aware of it. It implies work done can be written like T into delta A. So what is that work done or what is that energy release is T into change in area. Change in the area means small drops together will have bigger area than the big drop. So n into area of the small drops minus area of the big drop is the work done equation. So how much is that? That is T into n into, being a spherical drop, 4 by 3 pi area of the surface is, sorry, 4 pi r square is the area of the surface. So I have to correct it a little. So n into area of the small drop is 4 pi b square minus area of the big drop is 4 pi a square. Now we know the value of this En, right? So I will substitute this value from here. Let me just rearrange the terms. From here, N can be written like A cube by B cube. I'll call this as equation number 1 and substitute the value of this N in this equation number 1. So what we can say? From equation number 1, work done. So work done can be found as, from this equation, T, in the place of this n, let me write this value, a cube by b cube. The remaining value is the same, 4 pi b square minus 4 pi a square. So let's simplify this a little. 4 pi can be taken common from both of them. Then a cube, b square in the numerator and b cube in the denominator. Therefore, I will be getting 1b minus, I can get a square. So I can take 4 pi a square also common from these two terms. That will become a by b minus 1. So t 4 pi a square of a minus b by b. I have just calculated this value. So this much of the work is done and this much of the energy is released. So this is the part of the problem. Let me go back and read the problem for you once again. Yeah, that's it. So what he said is, a large number of identical drops, each of radius b, are combined to form a big spherical drop of radius a. I have taken that into consideration. These are all the small drops. This is the big drop. As mass is conserved, I got a relation between them. Then the energy released in the process. So I have calculated how much energy is released in this. I have substituted this relation and I found this value. This value. Right. And let's read back the problem. What's the problem says? The energy released in this process is converted into the kinetic energy of a big drop formed. Who is the big drop formed here? Is A. So what we can say is the kinetic energy of the big drop must be equal to the energy released in this process. This is what we have calculated, right? So let me just do that. We said the energy released. So the energy released in this process is the same that what we have measured just now as T 4 pi a square of a minus b by b, and kinetic energy of the big drop is half mass of the big drop into velocity square. We need to calculate the velocity of that big drop, right? So what is the mass of the big drop? Let me try to calculate. Half mass can be written like volume into density. Volume of a spherical drop is 4 by 3 pi. Big drop radius is a, 4 by 3 pi a cube. Mass, that's volume into density into v square. That's the kinetic energy. This is equation number x. You can call this is equation number y. He said this energy released is equated to, is generated as kinetic energy. So you can just equate these two equations as per the given problem. So what happens if I equate T 4 pi a square of a minus b by b is equal to, this is the equation, half 4 by 3 pi a cube density velocity square. So what can be cancelled? 4 pi in the numerator can be cancelled. Here is an a square, here is an a cube, therefore one a square will be cancelled. So a is remaining on this side. So what is remaining there? T 4 pi a square already got cancelled. A minus b by b is equal to, this 4 already got cancelled. This one. So 1 by 2 into 3, that is 1 by 6. Pi got cancelled out of this a cube. This a square is cancelled, so only a is remaining into density into velocity square. You want to calculate velocity. That implies velocity square is, take these terms to the other side. 60 a minus b by b. Take this a and d into the denominator. of the other side. This becomes V square. That implies V square is 6 into T by density A minus B by AB. I'm just writing terms A and B together. That implies velocity of that big drop and is under square root 6 TD A minus B by AB. See, the problem looks like lengthy, but it's not actually lengthy. The concept that we have used is very simple. So if you relook at the problem itself, so what you are trying to calculate, the energy released in the process, this is very important, is converted into kinetic energy. So I'm using a conservation of energy. So I have calculated what is the energy released, what is kinetic energy, and I have just equated both of them. To get into that relation between the small drops and big drops, I have calculated using the conservation of mass. That's how we have to solve the problem, right? And this is the way that you get an answer, right? Thank you for watching, and I will see you back in another video.